All right, well, I think we'll go ahead and get started. Is this a smaller audience than usual?
Smaller, a little smaller.
It's a little smaller. I see. So it's been a sort of a declining slowly over time. So this should be a conversation. So feel free to interrupt. I will be happy to talk in more detail about some of the things I'm going to talk about. But I'm going to talk today about exascale computing. This is something that we have been working on in DOE for 5 years. That is to try to get an exascale computing program going. So we've had a lot of time to think about the problems associated with this. It is a big interdisciplinary project effort to try to figure out how to build exascale computers that are actually useful for scientists. And it is building on the spirit of Berkeley Lab. This is a picture of Lawrence's, the founder of Berkeley Lab, his original team. So he had, you can see I believe the scientists for the most part are there. This is Lawrence right here, sitting down here with the engineers and the administrative staff all around him. So anyway, he really viewed his Nobel Prize as a team effort. And that's what exascale is going to be about as well. So I just want to also point out that, because I'm going to talk a little bit more about some of the motivations behind exascale and more computing performance, and some of it's going to revolve around large data sets coming from large experimental facilities. The lab has 7 of these different, 6 user facilities that are including NERSC, the Supercomputing Center, and ESNet, which connects all the labs together and connects them to the internet and so on. But this is a picture of the advanced light source. That's the building that you can see if you're looking at the lab from an aerial view. And this is not actually a garage sale in the parking lot. This is a superimposed image of what the inside of the ALS looks like. I recommend going to visit if you ever have a chance to do that. The Molecular Foundry over there, the NSEM facility, and the Joint Genome Institute, so where they do a lot of have billions of genes that have been sequenced for studying problems in an environment and energy and so on. So I'm going to start with a few myths of supercomputing. The first one is that when people say, a lot of people equate the word computational science with modeling and simulation. They say, well, computational science, that means high performance modeling and simulation. And I think it is true that the emphasis within DOE has been on modeling and simulation, that they have viewed the main problem that DOE has in computing as modeling and simulation. And that is influenced by the fact that half of DOE, not the half that Berkeley Lab works on, but the half that Livermore, for example, works on, is about nuclear weapons. And since the Nuclear Test Ban Treaty in 1996, there's been no more nuclear testing, of course, in the United States. And what that meant was that DOE had to invest heavily in modeling and simulation because it's the only way to actually understand the nuclear weapons and to try to keep the stockpile safe. So the petascale computing program was certainly motivated originally by stockpile stewardship. And there's this huge increase in computing within DOE starting in the early 90s or mid 90s, around the time that the U.S. stopped doing testing. So this has been the emphasis within DOE is entirely on modeling and simulation. But I want to point out, and people talk about the third pillar of science. In fact, I might have talked about the third pillar of science, or Jim did it earlier in this lecture, in this class. But the way I like to think about it now is that really there's theory and experimentation, of course, are the two traditional parts of the scientific method. And because data sets from experiments are also growing, you also need computers. Gone are the days when you can just write down in your lab notebook the 3 numbers that you need based on the experiments. Instead, you have, as I said, 16 billion genes coming out of the gene sequencers that you're studying to try to develop biofuels. And so you need computers to do data analysis. So you need more computing performance, whether you're trying to do big data or you're trying to do modeling and simulation. The last point I'll make about this, so trying to rebalance things here within DOE, and we're seeing large growth in the scientific data sets even within DOE. But the other point I want to make about this, and I don't think I left this slide in, is that in scientific data analysis and big data analysis, part of what you're doing is building simulations to help understand the model. So modeling and simulation and data analytics of experimental data sets are closely linked together. I'll give a couple examples of that. So here's the Obligatory big data slide. So sequencer volume that's one of the places where DOE has big data sets. The Large Hadron Collider. So there's projects. Look at the Higgs boson, for example. Huge amounts of data produced by the CCDs inside of that very large experimental facility. They have to throw a lot of the data away right at the detector because you can't move it even out of the detector to any kind of a computing or storage system. So a big problem for science, I think, is that we're seeing this in the light sources. This is the advanced light source at the lab. There's a plan to build a next generation light source. Back of the envelope calculation says we need an exaflop computer running all the time just to analyze the data coming out of the next generation light source in around 2020 when that system would be built. So huge amounts of computing are required. We don't think we'll probably use the same algorithms we're talking about today, so many things will change, but just to give you a sense of what these data rates are like. But what will probably happen in a lot of these other areas is you'll have to throw data away at the source because the CCD technology is still improving at Moore's law pace, and the computers, although we know all the problems that we're having both with in the near future with Moore's law, but more and in the past we're having trouble with clock speed scaling and things like that. So the data rates coming out of these detectors are really high, and of course that's really true. That's what's also one of the things behind sequencers as well. So a big problem for science is if you're going to throw some of the data away right at the source, then what do you throw away? And the problem is then you figure out what you're looking for. You build in what are called triggers into these devices, and you only throw away you only keep the events that you think are interesting for the thing that you're looking for. For example, the Higgs boson. They're going through an upgrade at the Large Hadron Collider, so they've shut it down. The concern was if they had not found the Higgs before they shut it down, when they turned it back on, they were going to have higher intensity and higher energy levels in there, which would cause the data rates to be much higher. And if they were still looking for the Higgs, and now this is getting a little beyond what I understand from a deep technical level, they were going to have to keep the data rates very high, and they weren't going to be able to actually. They didn't know how they were going to handle all of the data coming off of it. Because they think they've seen the Higgs, they will actually be looking for other things that they can have other triggers for that don't produce the same rate of data. So the data kind of coming off the CCDs will be at a faster rate, but they will be down selecting at a higher level as well. So lots of big data problems in science. One of the myths of supercomputing is that we only use this for large hero simulations. You've heard a lot about a couple of these other areas. So there's a lot of data science that's from data analysis. You heard from Julian Burrill about cosmic microwave background. One of the things I think he probably mentioned, but just to remind you, is that when you're looking at this map of the universe, there's some things in that you can't see. You can't see behind the Milky Way galaxy. So what do? They run enormous simulations to figure out what's behind the Milky Way, and they fill in that missing data. So there's a lot of data in these things that are bad. I think the other thing he may have mentioned, and this is related to some other data that we collect, so there's a bunch of environmental data. You have to be really careful about noisy data, and I'll say a little bit more about that in a minute. The other thing you heard Christine Pearson talk about was massive numbers of simulations that people are doing for things like screening of materials, and this is coming up. This particular picture is from a field of computational, biology and chemistry, dynamiomics. Dynamiomics is looking at the dynamics of proteins and studying the patterns in the folding dynamics of proteins. And they've looked at things like amyloids, which are connected to mad cow disease and Alzheimer's, and they've figured out that there are patterns in not the structure of the proteins between the diseased and good ones, but between the dynamics in terms of the movie, in terms of how they fold. So and Valerie Daggett at the University of Washington has run tens of thousands of simulations, stores them in a database, and now serves YouTube videos, if you will, of the dynamics of proteins folding. So there's a picture of Christine's project, the one slide view, which I don't need to talk about anymore. Even in climate modeling, you heard Michael Weiner talk about climate modeling. He probably didn't talk very much about the reanalysis kinds of projects, did he? But one of the things, so how do you know the climate models are correct? Well, you could wait 100 years and figure out whether or not they predicted the right thing, but that's a little bit too late. So what you do instead is you look back 100 years and try to run the models forward from, say, the late 1800s and see if 100 years into it, they're predicting the right kinds of behavior. This is a project from Gil Campo at the University of Colorado who does, it's called the 20th Century Reanalysis Project. They go back, he has this international community of people that are going back and finding logs, buried inside of some library. There's naval, there's military data, there's data from ships' crews, because ships would keep track of the pressure and the temperature, sometimes the surface temperature of the ocean and things like that. So these are handwritten notes going back to the late 1800s, reconstructed the climate every 6 hours from 1871 until 2010, and I think we'll continue going forward. So, talk about noisy data. This is very noisy, very incomplete data, but they have it mapped around the globe every 6 hours and also in 3 dimensions. And he said that they used about 10 million hours of computing at NERSC in addition to some time at Oak Ridge in order to do this reconstruction. They can't see some of the ocean eddies, and they can't see cyclones right now in that data. And the reason is, if you think about it, what they're doing is they're sort of averaging out the data, because there is bad data in the raw data that they're starting with, so that those things get sort of thrown out in the averaging process. So the problem is that a cyclone, as it's starting, looks like bad data, and so it gets kind of thrown out. So he said if they had about 100 times more powerful computers, he thinks they could actually reconstruct the data with the ocean eddies and the hurricanes in it. So there's a lot of data that comes up in science, and I guess this last slide just summarizes some of the projects that we have at the lab that have very large data sets associated with them. The data is big, so I calculated this actually when Jim was telling me that what the I guess the Facebook rate is, and I think it's about the same. So we measure it in petabytes per month. So NERSC gets about a petabyte a month of data that comes in from different scientific sources. That's in addition to the data that is computed internally. ESNet, the science network that connects the labs together, transfers about 10 petabytes a month, and that rate, these rates are growing exponentially. That rate in the network, by the way, is twice the commercial rate of what network growth is seen. So the internet, the commercial internet, is sort of leveled off somewhat. It's not growing at that kind of a high rate anymore. There's over 9,000 users that come in and access the data sets from some of these specific projects that you can see here. So there's Materials Genome, 3,500 users. They've only been online for about a year and a half. This is data from China, a project called Diabei, which is looking for neutrinos. And so the data comes from China to NERSC, and some of the data from the Large Hadron Colliders, the Atlas and the ELISE projects. There's different detectors and different projects there. There's the Planck data that Julian talked about. There's some carbon flux data that comes from sensors that are spread all over the world. So Deb Agarwal works on this, and one of her problems is also noisy data. These sensors are distributed all over the place. One of the problems they have is bird droppings. Birds come and drop stuff on their sensors, and you get a spike in the signal, and so they have to go and clean that stuff out. Literally, in the they're clearing it out in the virtual data set. Now, the interesting thing about this, just a minute, don't kill my punchline, Jim. So he knows too much. So Deb says, yeah, those bird droppings, that's a real problem. We have to throw out all of that data. But Julian talked about what happened early on, I think, in the cosmic microwave background, when they had these satellites where they were taking images of the background, and they said, oh, there's these weird patterns. We think it's the pigeons, right? So they get rid of the pigeons, I think twice. The first time they moved the pigeons away, cleaned out the satellites.
Telescope, yes.
The radio telescopes, right, sorry. And then and then the pigeons came back, so they got rid of the pigeons more permanently, and then they cleared out the radio telescopes again, and then they still saw the noise. And of course, that was the scientific discovery, right? The noise was not the droppings. The noise was the cosmic microwave background pattern. So, the lesson here is be careful what you throw away in your scientific data set, because it may not be noise, it may be actually science. This is, there's all kinds of weird data in here, and the question is, I'm kind of thinking people are not even going to log into systems like NERSC in 10 years. They're just going to come into web interfaces like the Materials Genome interface and say, oh, I'm interested in these materials, and some of the data is already stored in the database, and some of the queries that you run are going to generate a bunch of simulation jobs that will go off and run. So some of the queries may take a while. Okay, myth number 3. So because you've already had a lecture on clouds and you know that clouds are great, I figured we have to have the other view of the story. The myth is that supercomputers are expensive and clouds are cheap. So we did an estimate of what it would cost. First of all, we did an estimate taking some of the NERSC benchmarks. We shrank them down because we said, okay, well, we're not going to run our big petascale simulations in the cloud, but maybe we could run small, say 200, 100 to 200 way jobs. And so these are scientific applications run at this smaller scale, and we ran it in Amazon EC2. This is the slowdown that you see from running those applications. Paratech, oops, the C dropped off here. Paratech is this one, it's a factor of 53 slowdown. Why is that? It's doing a big 3D FFT, lousy thing to do in an Ethernet network, and so you really see a significant slowdown. Now, so if you use this as kind of your model of how things are going to perform in the cloud, and you say, yes, question back there.
Was this before or after Amazon EC2 went to the 10 gig Ethernet on some of the nodes?
This was the older 1 gig Ethernet. Okay. We did redo the study on the what they called their cluster service, which had the 10 gig Ethernet and also had dedicated compute. So you would get a whole node, much more expensive. To use that service, but you do, some of these numbers do come down quite a bit when you have the dedicated network. There's a lot more details. There's a report called Magellan that goes through this in detail, and they did determine that the two biggest factors in here are the network hardware and the network software. So the TCP protocol, even when they ran it over an IB hardware, it was still really slow. So using InfiniBand rather than at least a 1 gig, I'm not sure. I don't think the 10 gig got you all that much, nearly as much improvement as when you went to an InfiniBand protocol. But that one I'd have to look up for sure. And then the other thing is virtualization. So you do lose some from virtualization, and even if you don't have any sharing actually going on in the nodes. So if we tried to use, so NERSC's annual budget, the time we finished the study, about $57 million. That's been pretty flat for a while. It's hopefully going to go up next year, but we'll see. And the cost, if we estimated, what our total application performance capacity was over a year, it would cost about $900 million to go and buy that time in the cloud. Now you can say, well, they have better networks, they're better models that the cloud could run. It's true if we just went out and said, well, we had about 1.38 billion, a little over 1 billion core hours at NERSC in that year, and we could, if we just went out and bought that many core hours, it would cost about 181 million. So still a lot more than the 60 million or so that it costs that we get at NERSC. And right now the piece of the budget that NERSC spends on hardware is about 20 million a year. So just to give you an idea of the cost of that. So people think these supercomputers are expensive because you're buying them all in one place. Google and Amazon don't tell you how many millions of dollars they're spending on their computers because they tell you about it in 10 cents per core hour, which sounds really great. By the way, these estimates of, up here do not include the cost of the consulting staff, the account management staff, software licenses, the network bandwidth and everything like that. A lot of the other support is in about the other 2/3 of the budget. So why is this? Well, first of all, NERSC runs at a much higher utilization even than the clouds. It runs at over 90% utilization. Typical numbers for utilization at NERSC are about 96%. So that means 90% of the processor nodes are busy running scientific jobs. Exactly what is happening with those nodes is not something we really measure. But the biggest factor is there's no profit. And you can see that because in this time period when we were doing the study, or we were doing it in 2011, in that period between 2007 and 2011, the cost per core hour at NERSC dropped by a factor of 10 because we went from having about 100 million core hours per year. We had about 10,000 cores in the center at the time to having actually it was about 20,000 cores in the center to having 200,000 cores in the center. So it was Moore's law because it was turning into more cores. So that cost dropped by a factor of 10, whereas at the same time the Amazon pricing dropped by 15%. So Amazon, I think, was making money to begin with, and now they're making a huge amount of money. I talked to somebody at Microsoft, and they said they put a lot of money into the cloud services that run Bing, because what are they trying to when they're trying to take over the market with Bing, it is you're trying to get response time, right? So you've got to make sure that the computing is available when one of the users comes in and needs it. As you know very well from using NERSC, the difference is that we make users wait, and so you pay more for the cloud services because you get immediate response time, but that's not the way the government tends to allocate computing time for scientists. Basically, I don't think that the government cares very much about the productivity or the time that scientists waste. It's just not built into their cost model. They care about the machines being used. So myth number 4 is that data analysis is really easy. What I mean by this is you can do it all with MapReduce. I was at a meeting earlier this week with Mike Stonebreaker, who does, of course, it was well known in the database area, was talking about this as well. And he said, well, 5% of your data analysis workload may be in MapReduce because it's all the embarrassingly parallel stuff. The other 95%, you need things like LAPACK and ScalaPack. So what I see happening in terms of how things are programmed is, modeling and simulation. Most of what we do is write this stuff in MPI. Why is that? Well, because we're simulating physical systems that have a lot of inherent locality in the thing you're simulating. You can, even if you have to run a complicated graph partitioner, you can divide these things up into pieces with a lot of locality in them. So you can compute locally, and then you do some send and receive. So this kind of a bulk synchronous model works reasonably well. For a more irregular problem where you're trying to do some computation on, for example, a web connectivity graph or a Twitter graph, these are social networking graphs of various kinds, you need more of a random access model. And I may have said something about this when I talked about UPC, but these are very irregular problems. So what we see in things like the genomics area, some part of the workload, we're running massive numbers of independent jobs. We run blast jobs, and they can run on basically any network. In fact, and that was the last point in that cloud study, is the blast workload runs just fine in the cloud. And then there's a part of it where you're doing something like assembly, and assembly is where they go out and buy big fat shared memory machines because you have this very irregular access pattern. The question is, how much data can you squeeze into a single shared memory, or in this case a global address space? So I kind of look at modeling and simulation as having lots and lots of nearest neighbor computation, some amount of all-to-all communication that we know from things like 3D FFTs, and data analysis has massive numbers of independent jobs, which, by the way, also come up in modeling and simulation, and then some really hard random access stuff that tends to not come up in modeling and simulation. Okay, so that's a little bit of the background. How do we get to exascale? Well, there's a performance graph, historical performance graph that looks at, these are not top 500 numbers in this particular case. These are numbers from what are called the Gordon Bell Prizes, which is a prize given out every year at the Supercomputing Conference to somebody who runs a real application. Jim was on the, I guess, chaired or was on the committee for a number of years. So these are highly optimized applications, but they are real applications running at very large scales, a whole bunch of different problems, chemistry and materials and things like that. So that shows you the growth, and if you just connect this together, of course there's an exponential here, and you hit an exaflop in about 2020 that says just by doing kind of what we've, continuing what we have done in the past, we need to be able to get to an exascale. And certainly there are science reasons that you've heard in other lectures in this class in terms of what people need more computing for. So what happened over this time frame? Well, in the early 90s, there was Attack of the Killer Micros, and then in the mid 2000s, around 2004, 2005, multi-core, and everybody else started doing parallelism that they hadn't been doing before. And now we call the next transition maybe Attack of the Killer Cell Phones, because we really need to go to some kind of low-power processor. So I'll say a little bit more about that in another slide, but this is where we see a big transition happening, not at the kind of in between the nodes, but within the node in terms of the kind of processors are in there. And by the way, if you replace the red data that I had before with top 500 data, you basically get the same curve. And so people often complain about the top 500 number as being particularly skewed. I would say in both cases, what's really important is how much effort you put into tuning these applications, and on this kind of a log scale, although you don't always get real applications that run at the same performance as LinPack, you do get sort of the same kind of historical trend. Okay, so the big challenge in getting to exascale in a single slide is about energy. So the amount of power that we use in the Hopper system that you're familiar with is about 3 megawatts. So that's 1 petaflop. It was installed in 2010, uses 3 megawatts. To give you an idea of how much that costs, it's about $3 million a year in electricity, roughly speaking. A little less than that when we move to the hill here because it's a little bit cheaper power. But if we built an exaflop, of course, using the same technology, it would cost a few billion dollars a year to pay the electrical bill, which is well outside of our budget. You say, well, but that's not fair because you're not going to build one until, say, 2020. But if you look at if you actually look at Moore's law, which does give you energy efficiency gains with each technology shrink because the wires get shorter and so on, you can build the system in a much smaller package. You can. It was estimated that you get to about 200 megawatts. We can argue about the details of the numbers, but order of magnitude, that's what happens if you were to try to build an exaflop with the same technology, but about 10 years later. So, and this problem, by the way, is true whether or not you were trying to build 1,000 1 petaflop machines or a single 1 exaflop machine. You still had this problem that it was going to cost, say, $200 million a year in electrical costs for those 1,000 petaflop machines. So the first thing you do is say, well, we can build more energy efficient processors. This is a picture of the Intel Nehalem quad-core processor on the right. This is a Tensilica cell phone processor on the left. So the visuals are roughly to scale, so that gives you an idea of how what the relative size is, but maybe more importantly, this is a 100-watt processor, and this is a 0.1-watt processor. So there's a factor of 1,000 difference in the amount of power that is needed by the two of those. On the other hand, there's about a factor of 10 in the other direction in terms of performance. So this is a 50 gigawatt, and that's a 50 gigaflop, and the other one's a 4 gigaflop processor. So you multiply those together, and you say there's about a factor of 100 in energy efficiency advantages from the cell phone processor. You talk to cell phone designers, what are they primarily concerned about? They're primarily concerned about power because they're worried about battery life, and they're also worried, to my surprise, in talking to one of them, about heat. They're worried about the fact that you do not like to carry hot cell phones around in your pocket very much. It's rather uncomfortable. So, that is their primary design constraint, and we think with exascale systems that will be the primary design constraint as well as power in the system. So, we know that graphics processors, which have little tiny cores on them that are much simpler, or embedded processor cores, give you this kind of energy efficiency advantage. Now, this leads everybody to say heterogeneous computers. We need to have compute nodes that have these accelerators attached to them, that have these energy efficient processors like a GPU tacked on the side. The Titan system at Oak Ridge National Labs is one of these huge Cray systems that looks a lot like Hopper, except that every node has one of those AMD processor chips in one socket, and it has a GPU in the second socket. So why not just go entirely to small scale cores? Well, energy efficient cores. The answer is, well, we need those energy cores for, and SIMD, kind of really simple kinds of parallelism for energy efficiency, but you need a few CPUs to run the operating system and for the speed of some kinds of the parts of the code that don't map very well, or at least that's the argument. So that says, okay, well, we have to go heterogeneous. We'll need some fat cores and some thin cores. We actually are heterogeneous already in a system like Hopper. This may not be completely obvious, but the compute nodes that you run your jobs on are a little bit different than the I/O nodes or the service nodes in the system. The service nodes run a full Linux kernel. They can have slightly different versions of the processor cores, and most of the nodes in the system that are the compute nodes, and so so that system is already heterogeneous at the level of nodes being somewhat different, but not within a single chip. And so now we're talking about within a single shared memory space being heterogeneous. The other thing that people sort of equate with heterogeneity is a local store explicitly managed memory hierarchy. So it's more efficient. So if we're really worried about energy, you don't want caches in there, which are under hardware control. Caches move data up and down the memory hierarchy in anticipation of what it thinks that you need based on a pattern, but it may be moving data unnecessarily. The cache lines may be too large, and hardware prefetchers and things like that may anticipate incorrectly. So local store software managed memory hierarchies are more efficient, but a lot harder a lot harder to program. This is, to me, should not be equated with heterogeneity. It's an orthogonal issue, but it tends to be the case today that GPUs have these kind of local store memories, and so people kind of conflate the two. A split memory between the CPU and the accelerator. Not necessary to have that in order to have heterogeneity, but it is the way the systems are built today, where you've got a CPU in one socket, or CPU chip in one socket, and an accelerator in the other, and you've got a PCI bus, for example, between the two. This is because the GPUs were designed for a particular part of the market where that model worked, and the CPUs were just trying to keep up with the Moore's Law payoffs and getting faster and faster processors. So it's not clear how that's going to play out in the marketplace. And we know that the bus, these PCI buses between the two, are a significant bottleneck. The last thing, which I also want to separate even from the split memory interface, is that is the coprocessor interface between the CPU and the accelerator. So in most of these setups today, the CPU is in charge and the GPU is just running, particular loops or whatever that you've told it to run. And so you have the programmer has this model, which is everything is serial, that is on a single node, or at least in one of these CPU cores. And then they offload things to the energy efficient cores whenever you run into a loop or a loop nest that can do that. So these are the minority processors, the CPUs, and they should not be in charge. What we want is a model in which the energy efficient cores are doing almost all of the work, and if you have to have heterogeneity to run the operating system, say to access the file system, to run a full OS, then these energy efficient cores should call out to the more energy hungry cores and ask them to do some work on their behalf. So unfortunately, there's a concern that if we pick a programming model that works on today's heterogeneous energy-efficient processors by saying, well, it's an accelerator model with a CPU and a GPU, we tell everybody to use CUDA to program their HPC systems, then it'll be hard to ever get out of that particular sort of local minimum. Okay, so what happens? We started with our initially, say, 130-watt system. This is a particular back-of-the-envelope calculation. How much power was, that should be a mega in front of that watt. I keep copying the wrong version of this slide, but anyway, so that's 130 megawatts for the system that was just following Moore's Law curves. If we put in Manycore processors, we get rid of the big piece of the pie and get it down to about 75 megawatts, so still larger than NERSC's annual budget to pay the electrical bill, but we're certainly making progress. And there's lots of questions about what these architectures will look like and how they'll be programmed. But now the next obvious thing we have to attack is memory. So, all kinds of trends in memory are working against us. You may have seen versions of this slide, these graphs before. This is looking at memory density, which actually slowed down, although density is still increasing exponentially. It's not increasing at the same rate as logic, as the density of logic chips, primarily because I think that part of the industry is driven by other things, and the density is not the primary concern. People are buying chips for, they're looking for bandwidth more than they're looking for density. Cost of computing, is the blue line. This is data from IBM. There's the cost of memory, so also not dropping nearly as much. So what this means is that at a place like NERSC, people say, well, why don't you buy more memory in your systems? The answer is we already are paying, a lot of the budget inside that system is already going into memory. If we double the amount of memory in the system, there's just not that many other things that you can take out of it. And it's not as though you can just say, well, if it's 10% of the budget, we'll make it 20% of the budget or something like that. It's already a significant piece. So I know you've seen this graph before looking at energy, but all of the communication things are working against you. The cost of communication is not improving as fast as computing, and the amount of energy associated with any data movement off chip is much higher, 1 or 2 orders of magnitude higher than anything you do on chip. And so that is a real problem as we go forward to exascale, where we're now in a fully energy constrained design space. This is hard to change, right? The latency is really about physics. It's the time across the machine room floor if you're talking about the network. So there's not really much you can do about the speed of light. Bandwidth is all about memory. It is all about money. So you can buy more cables, but it is very, very expensive. And so if you don't need the cables, you certainly don't buy them. The memory wall here is, I think, an unfortunate phrase because it was kind of like we were moving along and we slammed into the memory wall. John Shelf once said to me, well, it's not really a wall, it's more like a swamp. And so I decided that was the right idea to have in mind. And of course, multi-core sometimes gets blamed for the memory wall because people say, oh, well, multi-core is making the memory wall problem worse. Multi-core didn't cause the problem. If we hadn't run out of clock speed scaling would have made the memory wall worse. But the truth is we're way into this swamp and we're just getting deeper and deeper as we figure out how to put more computing on the processors. So we make them all energy efficient, we put a lot more computing on chip, and we just have more memory problems. Now, there are things that you can do in the technology space. This is a project that John Shelf actually is working on with some people from Sandia, Micron, Columbia University, looking at things like optical interconnects, so on-chip silicon photonics, 3D stacking, of course, is a popular, there's a number of different groups working on that, and other kind of memory protocols that will give you better efficiency. There's a bunch of research questions associated, but this is one of the things that we're looking at for exascale. It's not clear how many of these will actually be available in the exascale time frame. So in addition to the technical questions, there's always market questions that come up. 3D stacking, probably yes. Optical interconnects, maybe not yet on chip, but we'll see. It may, around that time frame, these may happen. So if we get much more efficient energy, we can get this down. We shrink this other piece of the pie and can get down to, say, 25 megawatts. And so this is now getting to be a reasonable system, although it is still 10 times more energy required to run that exascale system than our petascale system Hopper. So what does that mean? So the way I look at it is we needed a factor of 1,000 in the number of, in the total amount of computing we could do from a petaflop to an exaflop. We're going to get a factor of 100 of that from more energy efficient architecture, which includes Moore's law, low power processors, and better memory technology. And we'll get the other factor of 10 by putting more power and cooling into the building. So that's sort of the back of the envelope calculation of how we'll get to exascale at NERSC. So one of the things that DOE has bet on in a major way is the idea of co-design, which is looking at really trying to influence the way architectures get built so that they're useful for science. I have to admit that one of my concerns, if you look back at that historical chart of what supercomputers looked like, back in the before the killer micros, they were specialized architectures just built for science, right? These vector supercomputers. That is a concern of what we're going to end up with is another set of specialized computers built for science. And the problem with it is they're very, very expensive, and it's not clear anybody can afford to build them anymore because of the cost of design and fabrication and things like that. But co-design is looking at, is not saying, well, let's build specialized architectures for science, but let's try to understand and at least inform the vendors very well about what kinds of architectural features make sense. And because this community, the high-performance computing community, is very thoughtful and introspective about performance issues at the architecture level, sometimes they can influence the vendors, not because the vendors care so much about that workload, but because they, as a big piece of their market, but because they are at least talking to people who have really thought carefully about these performance numbers. And I think Jim mentioned there was a speaker recently who said, from Intel, who said they were very surprised at the amount of influence the labs actually had on the architectures because, if you come in with data, you may be able to convince people. So one of the early projects of the lab, and this is Dave D'Onofrio, who left the lab and went to Apple, and who was working with John Shelf, was looking at one of these co-design projects. This was, if you think of what's kind of an extreme point in co-design, let's say we want to build an architecture specifically for climate. Did Michael Weiner talk about this project a little bit, Green Flash? Right, so this was, a full kind of, at least the atmospheric part of a climate model, looking at new data structures and algorithms that would have to be used at that level of refinement, then trying to understand the interconnect. They emulated the entire, the system on an FPGA, not an entire exascale system, but enough of the system that they could then run a full application code on the FPGA. So this is using ramp technology, and so you can at least run a simulator. It's about 250 times faster than a pure software simulator, and they were running the actual the actual climate code. And this gave them some confidence that you could build a machine that would be tailored for science. A climate model is a very general piece of code. So once you can run a full climate model on it that has all these different parts of the physical models that need to be in there for climate, you can actually run a lot of other applications on it. So you shouldn't really think of it in the same way you might think of the Anton machine for doing molecular dynamics. It's a more general purpose machine, but it's not arbitrarily for an arbitrarily broad workload. It probably wouldn't run integer and workload quite as well. So,
question.
Yes.
Can you sort of say that in the language of patterns? I mean, it's designed for the patterns that come up, computational patterns that come up in climate.
Yeah, so it's a good question. I think it is probably the computational patterns. It is also floating point intensive. So some of the things that they looked at the x86 instruction set, and they threw out a whole bunch of stuff that isn't needed for, that was in there for, what is it? Is it BCD? I mean, there's these things in there for doing banking and stuff that I'm not sure they're used by anybody, but there's a whole bunch of that for backward compatibility. But they also did things like turned off the cache coherence protocol, used a simpler memory model. They didn't have full MPI, but they built enough of MPI. And it was actually a little bit closer to it's kind of a queuing network model, kind of in between a one-sided put-get model and a full send-receive, two-sided send-receive model. So it was taking advantage of some of the patterns, yeah. Yes, Dave.
So I guess the other cool thing about Tensilica processors is that you can extend the ISA very
right.
easily. Did they do anything wild and crazy on the extension side?
I don't think they did anything wild and crazy. What they did was Tensilica, and they used to have this nice demo of it. You can go and basically click things, check boxes and say, oh, I want that feature and that feature, but not these other features. So I think it was more of a selection from a menu of options as opposed to kind of new features of the architecture. So work that Krista Asanovich and John Worsnick are doing to make it easier to build these kind of FPGAs. It is an ongoing project, FPGA emulators. It is a project at the lab, and so this is kind of an advertisement. If you're interested in getting involved, let me know, because I think a real challenge for these FPGA-based emulators is how much application work can we do, to what extent can we actually build these interesting architectural models that you might want for an exascale system and then try them out with the applications. And the applications people are not going to do the hardware design part, even the sort of selection of features part. So you want those wild and crazy ideas in there, but somebody needs to build the logic for them. So as I said, DOE has really bet on the idea of co-design, not necessarily all of it based on FPGA emulation, but just a lot of simulation at various levels of analysis of the applications and feeding that information to vendors. So there's some vendor partnerships in here. This is a project called, where is it? Well, anyway, there's these proxy applications, and this is part of the Exact Co-Design Center, which is a Combustion Co-Design Center, so they're looking at Combustion applications. And this is using the ROSE compiler, where they actually analyze some part of the Combustion code. They build this XML-based model. You feed in machine parameters and user parameters in terms of how you want to run the code and what the machine looks like. So think of Excel-based models at this level, not an FPGA-based model. They're using the or want to use the FPGAs to then validate that these other higher-level models are actually have reasonable parameters in there for things like the energy consumption and some of the performance details. And you can get dependence graphs and so on out of this. So this is work done by Sai-Chan and sorry, it's the Exasat tool. That was the name I couldn't remember. And Dietem Unat at the lab and some others. So, what have they discovered by looking at one of these combustion applications? They varied a bunch of these architectural parameters, and this is a simplified version of the code. The x-axis here is the number of species. So these are the number of chemical species. And in the combustion models, there's different ways in which you might want to run it depending on what the fuels look like and things like that. What they think at an exascale they want to simulate is around 50 species. So that's probably the bar that's the most important in this graph. But the point was that the application domains may demand different characteristics, which can really change your performance in some cases. So it's been a real problem that sometimes you take a benchmark, you run a particular workload on it, and then people say, yes, but that's not actually what we want to do. This comes up in climate right now. For example, there's a particular version of the climate code that runs well in GPUs, but it's not what they want to, and there's certain pieces of the domain that they do want to study that work well there, but a lot of the other parts of the climate code do not run well there, so depending on your workload, it may not work. So they looked at what happens if we put, they do some software optimization, so cache blocking, loop fusion, so these are the things down here. Then they combined it with some hardware optimization, so faster memory, so increase the memory bandwidth, a fast divide operation, which didn't give them much here, the green part. Fast exponentiation was really important because there's a lot of transcendentals in the code, and then a fast network interconnect, so on-chip interconnect with a higher bandwidth there. Gave them a little bit more payoff as well. So you can see these are the, this is the teraflop rate, so you're getting a substantial speed up here, maybe not quite a factor of 10 there, but a factor of 7 or so by going from the original code with both the software optimizations and the other features. One of the other things that's not clear from this data is they found that if you just did the hardware stuff and you didn't do the software stuff, you don't get all the benefits of the hardware stuff, so you need to do both together. Okay, so kind of to summarize some of these problems and what we're doing about them. Actually, this graph may be a little bit early, but power parallelism is going to have to increase by about a factor of 1,000 because we're not increasing clock speed. This probably means changing the architecture, and that means changing the programming model. There's these issues with memory, which also may affect the programming model because you're going to have it under software control. Resilience is one of the other problems down here at the bottom that I will talk about. But most of these problems are at the node level, so it doesn't really matter how big your system is. They're also happening already today. We're seeing GPUs and all these other kinds of processors, and there's the problem is that if you go with the emerging solutions, so things like CUDA, they can be harder to use. For the scientists are really reluctant to rewrite their code to use something like CUDA, and they're not very portable across architectures if you decide 5 years later that that's not the right programming model or architecture model and you have to go to something else. And not durable means that they may not last through future generations of the architecture because we don't know what they'll look like, but they are a little bit too specialized to the microarchitecture today. So you've heard all about auto-tuning, so this is one of the techniques that is being included in trying to get to exascale is writing these more specialized code generators. I'll just say that there are, and this is looking at the roofline model, which you've also seen, but I'll just say that as part of auto-tuning, one of the things I realized there's a fairly large investment in auto-tuning in the exascale program, or the exascale activities within DOE. There's a few different approaches that are being used. One is kind of the traditional Berkeley approach has been to write code generators using scripts. So whether that's using C or Perl, Python, whatever, there's something that's generating the code for a particular computational problem you want to solve. Then there's higher level representations, intermediate forms, if you will, of the algorithm that you're implementing, and transformations on that higher level representation. So that's used, for example, in FFTW and in Spiral, and then they generate code after they do these transformations. There's compiling a domain-specific language. There's a project at Livermore called DTEC that is doing that, that's in collaboration with some of the people here at the lab, Sam Williams and others. There's compiling a general purpose language, and the Xtune project, which is also a collaboration, is looking at compiling general purpose, think Fortran or C languages in order to, but putting auto-tuning ideas, so that is search-based optimization, into the compiler. And then a more dynamic online approach is what's being used in CGITS, which is a project here led by Armando Fox, which is on just-in-time specialization, and that's based on Python. So if you look at, you can also say it's a domain-specific language. It's an embedded DSL, which is done in Python, so Python plus some other stuff that's specific to your science domain, and then you do optimization on that using the introspection features that are in Python. So just to point out that auto-tuning has all of these different versions that people are working on. You've heard about communication avoiding algorithms, which I can think of in this context of exascale as trying to target higher level loops. Don't just optimize the kernels. You've got to optimize, not the SPMV operation, but the whole Krylov solver, or not just matrix multiply, the BLAS, but the entire LU factorization code. So since you've heard a lot more about that, I won't say more about it here except to just point out that it is also part of what needs to happen in exascale. The next sort of general thing we have to do is to avoid synchronization. So a couple of things are happening that are making people really nervous about the idea of any kind of global synchronization. And as you know from writing MPI code, you often do things like barriers, broadcasts, and reductions, which have either explicit synchronization or implicitly built into the barriers and reductions. There's a global synchronization point in them. So processors don't run at the same speed. They never really did run at the same speed because of cache effects, but they were close enough that we were able to use this bulk synchronous model. Because of things like dynamic voltage scaling, and this is data from the Intel Core i7 processor, and looking at how many cores are active and the variability that you get in the gigahertz, the processor clock speed, you can see that things are, there's some significant variability there. This other data, maybe even more surprising, is looking at the performance, and this is an application now running across 8,000 processors, and this is actually fairly old data, so I think those are dual core processors, so they're, you can think of it as basically a separate node, and what's for each one of them. And what is happening here is this is the running time of a particular phase of a bulk synchronous application, and this is how long each of the processors is spending in that phase of the application. So, they're not exactly all lined up, they're kind of wiggling around here, but pretty much this works okay except for these big spikes. So what are the big spikes coming from? Well, there were two different operating systems, by the way, because one of the big questions is, well, if we have heavyweight operating systems, they're going to have a lot more noise in them, so you're going to see a lot more variability in runtime. And so this was part of the argument for having microkernel-based operating systems on HPC systems, and there's a big tension there. But let me talk about the spikes first, which is these spikes were coming from ECC. They were coming from memory errors, and so they were being corrected because the ECC was doing what it's supposed to do, which is correcting the hardware level errors. But the ECC code, if you will, even though it was running in hardware, was slowing down those processors to such a substantial extent that you saw this huge slowdown in the runtime. I should say that the axis here does not start at 0, though, so it's maybe not quite as big as it looks like, but still substantial slowdown from a few of those processors. So what they found was that those processors actually the memory needed to be replaced. So they had the failure rates were too high, but that wasn't obvious to anybody because they weren't seeing system level errors. They were just seeing really high ECC corrections. Yes?
So I just want to check. These were static errors with a particular set of memory that just had an error with it. It wasn't a dynamic sort of occurring and disappearing problem.
It was a dynamic error that was coming up repeatedly because the memory was basically failing, if you will. It was memory that should be taken out and shot, which is what happened to it. But it wasn't. It was still in the system because it was performing functionally correctly because of the correction that was going on. But this is hardware level correction, which is still a noticeable effect. If you now talk about resilience protocols, which is what we're all thinking, oh well, because we might have more failures, we'll put in software layers to automatically correct for certain kinds of errors. You can imagine how much that's going to slow down the code. So if you're going to run that kind of dynamic error correction in software, you better not have a lot of barriers in your code, or you're going to be waiting for those slow processors that have been correcting errors for you behind. So if you take those correctness problems and you push them down at the system level, you're likely to generate performance variability instead of. So it's good to not have things failing, but you get really unpredictable performance. So we don't want to have a lot of synchronization. This is really calling into question the whole MPI programming model, and at least the use of a lot of barrier synchronization in it. I think I may have talked about this last time, but in some of the UPC work, and Jim may have talked about in the linear algebra stuff looking at plasma where you're doing dynamic task graph scheduling. It's the same kind of philosophy, which is get the barriers out of the code. You want to instead just run things based on the dependencies that exist in the code, and it gives you better performance on shared memory machines, and the UPC numbers are on distributed memory machines. So it says you want more of an event-driven execution model, much more complicated programming model. The bulk synchronous model is actually very convenient for these kind of problems for which it fits, but but because race conditions are not nearly as problematic, you don't have as many scheduling issues that you have to deal with. You just run things kind of in a single phase, and then you stop and do all your communication and so on. So what about resilience? Unfortunately, so I'm old enough to remember when we were talking about building petascale systems about 10, 15 years ago, and people were all saying, oh, these systems will never run, there's going to be too many failures in them. And in fact, when I took over NERSC in 2008, we had a system at that time that we did have a lot of problems with resilience. So what was the issue there? The network on that system, it was was not fault tolerant. So if there was any failure in the network, the entire system would go down. Okay, so yeah, painful. So so that system had a lot of failures. Hopper doesn't have that problem. In fact, we've had a different problem with Hopper, which is the system tends to stay up, and as a result, the job scheduler gets really fragmented. So after the machine has been up for a week, there are no more contiguous chunks of the machine in which to schedule big jobs. And so what happens is you schedule even a small job. Actually, it's even worse for the small jobs. They'll get spread out all over into different parts of the torus network, and therefore you can get performance instability. You get non-predictable performance results because you're kind of spread out all over the network in some of these small jobs. So sometimes when you're seeing performance issues, you should check to see where you're getting scheduled on that machine. And there is a feature that's supposed to be coming. I don't think it's installed yet. It's been coming for actually several months now, which is something to say, I really want this job scheduled on a contiguous piece of the torus. And the job scheduler tries to do that, but as the machine becomes really fragmented, it does less of that. So it turns in, once again, to that performance problem. So, we're really concerned that we're going to see a lot of this on these exascale systems. I would say the biggest problem right now in trying to even do research in this area is we don't know. So we know that because of hardware characteristics and trying to improve the energy levels, you're going to probably lower the threshold voltage. And so you're going to see more hardware failures from that reason. You're going to see more transient errors, and the hardware will fundamentally not be as reliable. Then if you want to run a really big job, the probability that something's going to fail with that much concurrency in it, and although I think that it really scales, the number of failures scales with the total chip area and the number of components, the failures tend to happen at all the connection points. But that these will be significant problems on these systems. But we don't have a very good model of what the failures are. If we knew what will be the biggest failures, we could probably design, have at least a research program to try to work on them. But we're not quite sure. In our experience, so in that system, Franklin, which had this characteristic of that having the network be not fault tolerant in this particular way. Once that Cray and and NERSC and everything worked to get rid of a lot of the kind of failures that were happening, so that the network was more stable. It still had this characteristic that if something bad happened, it could take out the whole network. The biggest problem we see now after the networks have been fixed is the file system software. So there's this big parallel file system. We run Lustre on the nodes. We have this remote file system at NERSC that runs to IBM's GPFS file system. So the biggest failure category when we look at it is something bad happens and the file system falls over. So it's not necessarily that there was a bug kind of directly in the file system that caused the original outage, but something bad happens in the network or in a memory, so there's a memory failure or something like that. It stomps on some piece of the network software and the whole file system falls over dead. So it's a problem. So there are research activities looking at this. Matan Erez, who is at the University of Texas at Austin, is working with some of the people at the lab, Eric Roman and others, on this idea of containment domains. It's more of a hierarchical model of a program, which is also what we may end up with because of that we don't want to have these barrier synchronization points. So the idea of a containment domain is you can actually kind of pick your own resilience techniques, whether you want to replicate things between nodes and then recover it. So we're looking at things like flash memory and storing things in flash memory where you may be able to go and get the data out even if the node has gone down. And then you can have different levels at which failures can happen. And so a failure that can be contained locally in a piece of the computation, that you recover from it at that level. And if you can't recover from it there, and there may be algorithmic techniques that you're using at some levels, then you'll propagate it up to higher levels, and then eventually you get up to the whole application. So the model that we have right now in Hopper, which you may have seen, is that if there is any kind of a hardware failure, like a node failure in that system, it takes out the whole job. It doesn't take out the whole machine, but it does kill the whole job. And so, of course, we expect all of the users to be checkpointing their applications if they're going to run for any substantial amount of time. One of the other things, which is in retrospect completely obvious, but I always thought of resilience as being a problem for very large scale computations, but it's also a problem for very long running computations. And in fact, in the biology space, this is one of the places Kristen Fagnan, who works with NERSC and the Joint Genome Institute, has put fault tolerance checkpoint restart into their codes, because they're not running at very large scales, but they're running for weeks at a time. And the probability you're going to hit a failure is just as high if you're running for a long period of time as if you're running on a long number of processors. It's kind of the total number of core hours in your job that really matters. It is, however, easier to checkpoint a small application running over a long period of time, because it doesn't take so much bandwidth on the entire machine, as long as everybody else in the machine is not checkpointing when you are. So anyway, this is ongoing work, and I think, unfortunately, I still think that a lot of the problems, bugs that we have, and things that are going to cause these systems to crash are in the software, not in the hardware. Okay, so what does this mean for this last slide that I skipped over? Is there's also work going on in operating systems. There's the tessellation project here on campus. And John Kubitowicz, and looking at this idea of kind of running an operating system that divides things up over the cores and isolates them between the different pieces, which also helps with faults. And originally this seemed like, well, maybe this is only a problem if you're trying to run a bunch of different kinds of applications on each node. One of the things that the scientists want to do is they want to be able to run analysis software at the same time they're running the simulations. Those two pieces of software were built entirely separately, so you might want to put those onto the same node and then partition things like this in the between those different applications. Okay, so what does all of this mean for NERSC? So this is what the NERSC workload looks like based on science domain over a period of 10 years. And so what can you see from this? Well, you can see that NERSC was historically a fusion simulation center. That was actually its name at the beginning. It was started at Livermore, and then it moved to Berkeley in the mid-90s. And so that, the percentage of time going into fusion has come down. And there's some other, I think there's some trends. You can see a few things picking up, but mostly you just see lots and lots of, what's that? Materials has picked up. Is that the orange one? Oh, and there's climate. You can see probably IPCC or something like that happening in there. But there's, it's hard to say, well, we can look at this and decide, well, we just need a machine that's going to solve a certain piece of this workload. And so we can try to build models of what things look like, but we're very unlikely to actually be able to capture everything in a simple kind of a model. So I like this quote from George Box. There's a lot of debate about buying machines based on the LinPack benchmark, which is something NERSC has never done. But there are sites the supercomputing centers that care a lot more about LinPack numbers. And so I've gotten into debates about whether the LinPack numbers are useful and should we even publish them. So some centers have refused to publish their LinPack numbers because they think it's such a bad way for people to look at performance of the machines. My feeling is, I'm a scientist, an engineer, whatever. I like to have all the data, so I'm happy to know what the LinPack number is on the machine. It does tell you some interesting things historically. It's not, I shouldn't buy a machine based on the LinPack benchmark, but it's still interesting data. So what does NERSC use instead? It actually uses this idea of the 7 dwarfs, or motifs, if you will, of scientific computing, and looks across the science domains and picks a set of applications that tries to cover this kind of a grid. And there's a much smaller set of application areas here. There's also been an analysis, and I think I might not have put this slide in at the right place, that although we have about 600 applications that run at NERSC, so it's really hard to capture that kind of a workload. However, there's about 25 applications that account for 2/3 of the workload. So 25 now we can start to kind of get our head wrapped around in terms of what do those 25 applications look like. And And these are picked from some of the, these are some of the science areas that have the most computing associated with them. And this tells you what their computational patterns look like in there. And so we pick applications, I saw that, so that represent that kind of a workload. And use these when we're doing procurement. So we look at kind of an average of the performance of these and try to buy machines that maximize that average. Also just mentioned that we have looked at the kind of libraries. We're getting some better data out of this, but and the motifs, if you will, inside of these codes. So this shows you that, FFT, structured grids, really popular. FFTs, also very popular. Of course, they're running unstructured grids, and dense and sparse linear algebra are there as well. So I'll just stop by saying that from a strategic standpoint at NERSC, we're looking at this kind of a roadmap of trying to install systems about every 3 years. Probably not going to quite make those benchmark numbers in terms of the size or the performance of those systems, but that what was our, the problem that we had, we were building and producing systems that were using MPI, flat MPI. With Hopper, it really is better to use a hybrid programming model, so MPI mixed with OpenMP. NERSC 7 is a system, Edison, that has, a piece of it has been installed now. I don't know if any of you have used it. It'll be an Intel-based machine rather than AMD-based machine. And so the problem we had with NERSC 7 is saying, well, should we go to sort of an energy-efficient Manycore model? And we knew that when we got up to exascale, we would need to do that because there was no way we were going to hit an exaflop by using a traditional x86 processor architecture for all the reasons I talked about. So the question is, do we tell everybody, reprogram your applications right now because we're putting a CUDA machine on the floor, and then maybe reprogram it 3 years later? And so the answer was no. As a result, NERSC 7 is only going to be a 2 petaflop machine based on traditional cores. NERSC 8, which is the next system, which will come in about 2015, 2016, is probably going to be a Manycore architecture of some kind. Whether it'll be a GPU or Intel mic or whatever will depend on what people bid on that. But that's a project we've already started working on that system. So that's just to give you some idea of how we expect to get to exascale at NERSC. Some people say we're too conservative by putting NERSC 7 on as a traditional machine, and some people say we're completely crazy for saying NERSC 8 is going to be something else. So I figure everybody's a little bit unhappy, and we're probably about right. So anyway, any questions? And I'll let you do your surveys because I think you're here for that. So any other questions or anything? Okay, thanks very much.